Hi, my name's Sam, and in these next couple of lectures we're going to be dealing with the imaging principles and technology that forms the ultrasound image that we see. And in this first part we're going to be dealing in particular with the ultrasound machine and the parts of the machine that are used to form the image and parts that we can actually control in that. I think probably this is not intuitive to me, and I think it takes me a while to try and understand this and have to go through this a few times, but I hope this is useful. So the ultrasound machine is made up sort of sequentially of different parts that each have an important role. And as I said, we've got variable control over some of these parts of the machine. We're going to start off by talking about the transducer, the transmitter, the beamformer, the signal processor, which leads to the image processor, and finally to the display. And we'll talk a little bit about the storage of the ultrasound image at the end. So the transducer. Well, I'm particularly talking about phased array elements from the echocardiography side of things, and typically you've got 128 elements of a transducer that are both sending out and receiving ultrasound waves. And as we talked about in a previous lecture, we have a voltage that's applied to the transducer, and this fires off those piezoelectric crystals which change that voltage into a pressure. That pressure is then sent out into the body, and when you get some acoustic variable interface, some of that pressure will then be sent back to the transducer, hits one of those piezoelectric crystals, part of the array, which change that pressure into a voltage, which is then sent back. And that information is sent back to the transmitter. So to make up the actual image itself, for something like a beam mode image or brightness image, this is the where it sends out these images at a different interface, and we form the image one section at a time. With something like an M mode image, we just look at one line on that sector, and we send out just one line of ultrasound energy that goes down, up and down that area. And obviously with a beam mode image, if you're sending out multiple lines, 128 lines for example, across a whole sector, you have to pick up all those different lines before you can move back to the beginning. So you have frame rates somewhere in the region of 30 to 50 frames a second. Or 30 to 100, frames a second. With something like M mode, where you're just looking at one line, you can get much more information in terms of temporal resolution. So you're typically getting frame rates of about 1,000 frames a second with M mode. But again, the problem is you're just looking down one line of sight. And M mode is what we had about 20, 30 years ago. That's all we had. So the transmitter is the part of the machine that talks to the transducer directly, and it generates that transmit signal to the transducer. It has some default settings based on what transducer you're using, and you can change these to a certain degree. But you're going to have a certain amplitude that's set, a frequency range that you could use, and that's going to determine the pulse duration that gets sent out of the transducer, which in turn is also going to be dependent on that the PRF. And that's obviously based on the pulsed echo principle, so that you have to, when you send out a pulse, that pulse repetition frequency is dependent on both the depth that you're imaging as well as the frequency of the transducer that you're using. So you're going to be able to control these to a certain extent. And that's using both power and frequency. So on the machine that I use, that frequency is on that multi-hertz button, and I've got a power button as well. But you've got to remember that if you are going to increase this power, that is also increasing the energy which is being transferred to the patient. And this is obviously extremely important when we start to talk about the safety concerns with ultrasound. Just a quick word again on frequency, as we've discussed. With lower frequency, we are going to get increased penetration. And you've got to also remember, with that pulse repetition frequency, if you are going to be changing your frequency, that is going to, that's going to make sure that with the pulsed echo principle, again, all pulses have to be sent out. All echoes have to be received before the next one gets sent out. So if you decrease your frequency, or you're limiting your depth of penetration, that is going to affect your pulse repetition frequency. So next in line is the beamformer. So the beamformer has both a transmit and a receive section. And this is all to do with electronic focusing. So again, we discussed in previous lectures regarding focusing of the ultrasound using electronic delays, which then fire off the arrays at different times, which focuses the ultrasound beam. And that happens both in transmitted echoes as well as received echoes through these variable delays. And in reality, you've probably got about 128 delays, both in transmission and reception of the ultrasound waves, leading to the beamformer. The beamformer will also be involved with amplification. So first of all, trying to remember again about the apodization. We talked about side lobes and grating lobes, which is when some of that ultrasound energy is sent out sideways out of the ultrasound arrays, particularly from the arrays at the edge of the transducer. So apodization was all about decreasing the amplification of sound waves that are received at the edge of the transducer versus the center of the transducer. And this is where part of that happens in terms of the amplification. As well as apodization, you're also going to need to have amplification of the echoes returning in general. So again, as we discussed in previous previous lectures, some of these echoes are going to be attenuated to a huge extent. So again, I'll use an example that we used in some of those previous lectures. If I had a 2 megahertz probe and I'm imaging at 20 centimeters depth, on average, the ultrasound sound waves that are received compared to the ones that are transmitted are going to be about 10,000 times less in amplitude. If I have a 3 megahertz probe and I'm imaging at 20 centimeters, it's going to be 1,000,000 times reduced in terms of the amplitude from transmission to reception. So in the beamformer, we're going to get part of that amplification process of those received echoes so that we can actually see the things. We've got a little bit of control over this beamformer in terms of both obviously the depth of focus as well as the beam direction. If you're using vascular ultrasound, for example, you can steer the image, or using a linear probe, for example, you can steer the image. And this is again where some of that delay in the electronic focusing or the electronic steering happens at this area as well. Of note, one of the things that you do not have control on this is the dynamic focusing. And just to recap a little bit on that dynamic focusing, that was the automatic sort of electronic delay that happens to compensate for the delay in returning echoes from different depths. And that's an automatic function. You don't have control of the dynamic focusing. You do have control of the focus position, obviously, on most machines, and obviously that's going to be directly related to some of that variable delay. Okay, so that's the transducer, transmitter, beamformer. Next in line is the signal processor, which is probably, I think, the hardest part to try and understand in the machine, and I'll try and take it slowly. There's a sequential format that happens to it. So first of all, with the beamform data, before it actually even sort of gets into this sort of the heart of the signal processor, there are a couple of processing things happen, which is the TGC, or time gain compensation, and the digitization of the actual image, which I guess is similar to what we use in DVDs or CDs. Once in the signal processor, there's a filtering process, an amplitude detection process, and dynamic range compression. And we'll talk about each of these in turn. So first of all, the time gain compensation, and I probably don't have to teach you too much about this. So this is operator-controlled amplification at quite a crude level, sort of from top to bottom of the image. It's probably the most commonly altered settings on the machine. That's why I think you probably know about it if you're watching this lecture. And it's all about the variable amplification that you control. So it's happening, as I said, before you actually hit into the main heart of the signal processor, and it looks something like this. So that you have images that are that if you change the time gain compensation, for example, on the left side, that's a normal image. In the middle, where we've got the time gain compensation at very low levels on the near field, very high levels at the far field, you have the black and white corresponding, and vice versa. If you move the time gain sort of arrows in a different direction. So next is the digitization. And this is a very important part of the process because it's all about how the computer can process the information. Because up until now, the information is in a voltage signal, and we need to convert it into an analog signal so that the computer can process it. This is where you're basically changing from an analog to a binary number. It's through an AD converter or analog to digital converter, and it's how we listen to music on CDs or MP4s. It's how we look at DVDs on our computers. So once we've got this digital information, we then need to start the filtering process. And this is all about how to try to get some of the noise out of the systems, try and reduce that. And all electronic systems are going to have some kind of noise, and it's like snow on the sort of old black and white TVs. And this noise is typically spread out over all frequencies. But again, we are going to be getting some information that's coming back that's going to be reflected, which is going to have some of this sort of low-level reflected sort of intensity. And that's going to maybe get interfered with some of the noise. So what we're trying to do is take out the noise and keep our low-level reflected echoes. And the way we start doing this at a very basic level is, again, we're talking about the bandwidth. And we know what the bandwidth is of our received echoes based on the operating frequency that we're transmitting at. And so we can look at trying to focus in on just that level and remove the low-level intensity echoes that are either side of that. So this is a first way that we can try and filter out some of that noise. And what this does is it just improves your depth of penetration as well as keeping some of those low-level reflected echoes. Amplitude detection is the next stage. And this is all about trying to determine the brightness on the display of each certain point. And what the machine will do is, looking at some of this digital information, it will determine, based on the amplitude, the strength of that returning echo. And that's, again, the greater the amplitude, or the greater the strength of that returning echo, the greater the brightness on the display. And what this will do through a process of what's known as demodulization is it's going to ignore all the frequency information and just focus on the amplitude. And that's where you can see on this green line, the machine focus on that green line as opposed to the blue line, which has more of the frequency information in it. So it's just focusing on the amplitude. Next is dynamic range compression. The dynamic range is essentially the range of echo intensities that are going to be processed, from the smallest to the greatest. And what we're trying to do is we are trying to put that into a display on the echo machine that we can see. And if you have a low-level intensity returning echo, that is black, and a high-level intensity echo is white. And typically, in terms of the received echoes that we're getting back, the range is somewhere in about 1 million if you were to put it in a ratio. So what we want to do is we want to try and put that in more of a workable format, because trying to put a range from 0 to 1 million is difficult for our vision, because our vision can typically only see about in sort of a typical range of about 1,000. So in order to try and put these into more manageable chunks, we process this in decibel format. So again, it's this ratio. And it's all about trying to put a large ratio into a more manageable ratio for our eyes. So what we're looking at is trying to change something like, with the echo intensities of about 60 decibels, we're changing it over into our visual eyes, which is more like 30 decibels. But one of the things we want to try and do is we want to try and put it so that we're getting as much information as we possibly can from that echo image. And that means that we want to, instead of having a linear kind of scale, we have this curved scale. So that means that maybe the first half of our scale is focusing on the soft tissues, and then the brighter echoes take up the second half. So here you can see on this scale where you have the echo intensity, range of about 60 decibels. We're going to compress that into our grayscale intensity on the y-axis there, which is about 30 decibel grayscale intensity. We make sure that the soft tissue uses the lower half of that grayscale ratio, and these stronger echoes take up the upper portion. To try and improve the image quality by cleaning up the image and reducing the noise or interference, we discard the lowest, maybe 20 decibels of echo intensity. And therefore, we try and get the best image quality that we can. Now, this dynamic range is going to be able to be controlled to a certain extent by the user, and there are buttons on your machines that will either be called compression or dynamic range or contrast or something. And that's all about messing around with this dynamic range. And here on this image, you can see that something like on the left side here, we've got something with a high dynamic range, which has this kind of more uniform image texture. But we get a lot of these, sort of high artifact echoes that are produced, as compared to the image on the right, which has this low dynamic range, and it's kind of got more of this pixelated high contrast, so more black and white image. But you do get areas where you get dropout completely, and you're going to lose some information. So somewhere in the middle of those two is obviously where you want to be. So that was the signal processor. Now let's focus on the image processor. And this is all about to try and, because the echoes are now ready to be stored and displayed, and this is all about how we can try and do that. There are four main areas to it. We've got the scan converter. We've got an area where we do a look at pre-processing. So that's before we actually store the image in the ultrasound machine memory. It's about how we can try and process that echo data to try and display it as accurately as possible. And after the image memory, then we can look at post-processing. So that's all about messing around with the image after it has been stored. And typically, that has some limitations because the images are obviously already been stored. So the scan converter is all about putting the image in a format so that it can be displayed. If you try and imagine the echoes being received into the transducer, they're all going to be related to a particular line of sight. So a certain array on the transducer is going to be related to a particular line of sight on the echo display. And what the image processor is doing here is just taking in those, taking in that information, which is probably in some more of a linear format, and it's telling the computer, depending on what kind of image probe you're using. For example, using an echo probe, it's saying that we've got that kind of sector format sort of appearance on the display. And it's saying that if I've got a particular line of sight, it's related to this particular line on the display, as you can see on this image on the sort of bottom right. What the scan converter is also going to do, it's going to say that as well as each sort of echo line being associated position on a display related to a certain area, it's also going to try and fill in some of the gaps. Because if you have this information that's coming in this kind of linear format, and then we're putting it into a sector format, there are going to be areas of the image that are not going to have any sort of echo information on it. And this is where a process called interpolation comes in, which interpolation is where you're kind of filling in the gaps between the scan lines with appropriate values. And so, for example, using this image I got off the internet, if the original image was of as you can see, of that sort of little stick figure. When we actually getting the information back, it looks more like sort of the middle image. The interpolation is going to be filling in the gaps so that we try and give the most accurate information that we can related to the structure that we're actually imaging. And it's all about just improving that image quality. Pre-processing. So this is all about trying to change the image prior to storage, and again it's about trying to get a sharper and smoother image. There are several things that they can do. I think the most important, sort of related to clinician knowledge, is about knowing about edge enhancement, and it does what it says on the tin there. You know, it's about recognizing these tissue edges and trying to smooth them and enhance them. You've got persistence, which is about taking the most recently acquired image and averaging it compared to previous images. And it's again about sort of smoothing out that image motion and smoothing out the sort of speckled texture that you're getting between the images. Compound imaging. So with the steering that we're getting done by the Beamformer with that variable electronic delays, you're going to be looking at a structure from lots of different areas. And what you can do is that if you're steering it in lots of different directions, you can try and combine some of that information, looking at that same structure, but looking at it from different areas, as you can see in this diagram here. And it's putting all that information and compounding it together. Again, getting a smoother, sharper image, trying to describe it as accurately as possible. Finally, it's important to know about right zoom. Okay, so you probably all use the zoom function on your Echo machines, and there are two ways that you can do it, and it's either pre-processing or post-processing. And pre-processing is preferable. So pre-processing zoom is also known as right zoom. And that means that before you're actually storing the image, you are focusing in on a particular area. So here on these images, you can see we've got a two-chamber view in the middle, and on the left, we've got a right zoom. And that is where actually, whilst you're taking the image, you focus in on a particular area, and you're asking the machine to ignore all the other information. You just want to be focusing in on that one area. And if you're doing that, that means that you can have reduced lines of sight, you can have reduced depth, and as I hope you're picking up from that, you're going to have improved frame rate, and that means you're also going to have improved temporal resolution. So if you're using this right zoom, the pre-processing, ignoring all the other information, just focusing in on that, and with a bit of eye of faith, maybe I can persuade you that the image on the left is a little clearer than the image on the right. And in terms of the frame rate, you've got frame rates that are much higher when you're using right zoom compared to if you're using read zoom. So on read zoom, it's where you've actually taken that image, you're looking at it on the display, for example, it's already been stored, you know, your probe's not on this patient's skin, and then you can take a sector and you focus in on it. And what you're doing there is obviously you're just focusing in on the already stored information, and you're just zooming up the pixels. So you're not going to have such good resolution. The frame rate is going to be the same as the original frame rate, so it's not going to be as smooth or accurate. In the image processor, we've got the image memory. So this is all about how we're storing the information. When we're displaying the information, it's obviously all about a pixel with different grayscale appearance. Our eyes can only determine a certain dynamic range, as I discussed, of around about sort of a ratio of about 1,000. And so the image memory is all about trying to store information. And again, it's in a binary format, and trying to describe a grayscale format that's got about a ratio of 1,000. So each pixel is going to have a corresponding line of sight, and each one of these pixels is going to have a certain number of binary digits that are going to describe a grayscale format. And that grayscale format, again, is in about a sort of 30 decibel range or 1,000 decibel range. So using a scale, you can use binary numbers to describe certain values. Okay? And this is where I use these binary digits, or what's known as bits, to try and describe these numbers. And it's almost like if you can imagine having a number of different layers to a number of different layers to the image. And depending on how many ones and zeros, it gives you the grayscale average. So we talk about the number of bits, and that's related to the dynamic range. We typically have in ultrasound machines 8 to 12 bits. And that can typically describe, if you have 8 bits, that can describe about 256 different levels. Or you can have 12 bits that can describe about 4,096 different levels. And that can describe about a 30 decibel range of echo frequencies. So I think from my point of view, obviously I think it can obviously get more complicated than this. Just try and remember that the image memory is stored in binary numbers in a digitized format. There are different levels of bits. You either have 8 to 12, and that can describe the dynamic range that our eye can see, which is about 30 decibels. Finally, post-processing, we've discussed the read zoom, which is obviously just focusing in on the image that you've already got. Color mapping, we love the blue hue. You can show whatever hue you want. It can be red, gold, whatever, black and white. In our hospital, as I said, we like the blue hue. And you can also use this post-processing for certain measurements that we have. Finally, the display. So the display is just a high-end computer display. It's trying to show the maximum number of pixels corresponding to the particular lines of sight. And the high-end computer display means that you can also display a certain dynamic range, and that's what we're trying to show in as greater detail as possible. So I think that's probably all we need to say for the display. In terms of the storage, it's getting better and better. You know, previously we were having to print it out onto either pieces of paper with the M mode back in the sort of 1970s, onto the video that we saw in the 1990s, and now obviously we're moving much more into using digital memory, either stored on networks or CDs, DVDs, and it's just simply getting better and better, and we're being able to store more and more information. So in summary, the ultrasound machine is made up of different parts connected in series. We start with the transducer, that is taking voltage information, turning it into pressure information, receiving pressure information in the form of echoes, and turning them back into voltage with the piezoelectric crystals. That information is then sent to the transmitter, which is actually driving some of the transducer originally with its voltage information, and transferring it to the beamformer. The beamformer has transmit and receive portions, and that's all to do with the variable delays and variable amplification of that voltage signal. That voltage signal is then sent from the beamformer to the signal transducer. It goes through another operator-controlled amplification in terms of the time gain compensation, or TGC, and the information is digitized and enters the signal processor. In the signal processor, we have filtering out of noise. We change it so that we've got amplitude detection, and then it's taking that range of different amplitudes and it compresses it in the dynamic range compression. And it compresses that range from about a 60 decibel into a 30 decibel range. This digital information is then sent to the image processor, and the scan converter will take that information, and it takes those particular lines of sight and matches it up with a particular area on the display. And then you enter pre-processing, which is all about trying to sharpen up that image, both through edge enhancement, persistent, compound imaging, and it sends it to the image memory. That image memory is made up of those different bits, typically between 8 to 12, which is trying to use that digital memory to accurately display as well as possible the grayscale image on the display. Before it enters into that display, you can do a degree of post-processing with things like measurements or read zoom, as we discussed. And then finally, it goes into the image display, which is essentially just high-end computer imaging. The image can either be stored on the machine, or it can then be transferred elsewhere for external storage, such as DVDs or external storage machines in terms of internet storage, etc. So that's it. I hope that was useful. Thank you very much indeed.